So did anyone look up the Coriolis effect? No? Anyone? No? Okay, I did. So, so I have to correct myself as a result, because it's not exactly what I said. So even though it is a valid effect, it is not what we see in the bathtub or any other drain, where the water is going down and rotates, and it's not really because of the rotation of the earth, because it's just not enough apparently force in order to create this whirling effect. And even though in the lab conditions they did create it, and you put the water in a very still position, very perfectly drain, and then eventually they wait long enough, they do see the rotation. Okay, and it comes directly from rotation of the earth. So it is a valid effect, but what we see is actually simply imperfections of the bathtub, and so the water comes in from different directions at different speed, and that's what creates rotation. So it would be an accident, I think, that if they will all go straight down. Okay, so if they're not going straight down, then what is the choice really? It's not like they can rotate in all different directions. Right, so there's some imperfection of the direction with which water comes into the drain, which means that it will go off on some kind of diagonal direction, and since it's sort of the particles push each other, they kind of coalesce into one stream that creates this whirl. Okay, so that's what creates it. It's like this, maybe. So you can imagine that whether it is a funnel or anything like that. So it's or upside down, doesn't matter. So you can imagine that certainly that the particles will be kind of sliding down in the exactly vertical direction, but only if they start sliding in the perfectly vertical direction. You can easily imagine that early on it's not a particle that just take it. It's a little ball, and then you just turn it sideways a little bit in the beginning. You give it a push. Okay, so it will go like this, and it will go behind, and it will have it will make not a circle, but rather spiral. Okay, so it will spiral into the drain, either this way or upside down. Okay, so and then well, first of all, mathematically it doesn't matter really. So even though the effect is real, so mathematically it doesn't matter. The fact that apparently the Earth does not rotate fast enough in order to create it, to make it significant. But mathematically we imagine that we are on a different planet, and the planet that does rotate fast enough, and then it will be produced. The effect will be produced by rotation. Period, not by anything else. If the rotation was fast enough. Okay. The point, at the same time, the point was being made is that primarily the example we were considering was the rotation within the circular rotation. This one, okay, not this one, but the other one, circular rotation. The other one. Okay, and so why it cannot be reproduced? So circular rotation, why it cannot be reproduced by just force of the gravitation pulling it down. And the reason was, well, it's kind of easy to imagine probably. If you can you imagine that water going down the drain or down any kind of surface, and it makes imperfect circles on the same level. Okay, so it certainly is impossible. You think conservation of energy, if you like it. So it will have to go down. If there's any kind of pull down, it will go down. Okay, so that reasoning applies, even though very informally. The formal way to discover that is here. We just try to find that function, the shape of the surface, and that down which the flow goes, and then there's no such thing as we have discovered. We will discuss this later today. And once again, this is a misleading picture because it is an approximation, so it gives you an impression that it is a world, but in reality it is circles. Okay. Okay. So any questions about this? Okay. So, and we're looking at something quite complex. It is the algebra derivatives, and just the same as in calculus 1, the same point of view that we are looking at, even though the differentiability is much more complex. The derivative is not a limit. Look at it. The derivative is that function. I'm sorry, that vector m vector m which is defined through this complex limit, but that vector is defined indirectly through this property, and then only later on is discovered to be equal to the gradient, which is defined as not a one limit but several limits in different directions. Okay, so and then we proceed to this really productive way of looking at derivatives as rules that give you how algebra interacts with differentiation, and how you can have all those shortcuts just like in calculus 1. So these are the main rules. They look exactly the same. They're very predictable in the I'm not sure how predictable they are actually, so that I'll address in a minute. And then the product and the quotient will look the same, but they are more complicated. As you can see, you have to read carefully these entries because some of them are vectors or vector fields, depending on whether you're looking at one vector, one location in time, or all of them simultaneously. So one location in time, the derivative is a vector. If all of them simultaneously, it's a vector field. Okay, and then but the derivative, but g, the function itself, say over there, is in fact just a scalar function. Okay, so that way you multiply vector by a number, and then you have another vector. So altogether, then you have the matching of the. I'm not sure if you have had that discussion in calculus 1. Which is the naive product rule. Remember this one? Is it familiar? I'm sure nobody taught you this. It's just it's a mistake that is made commonly in the beginning of calculus 1. Differentiating derivative of differentiate the product, just differentiate multiply the derivatives. Okay, so almost everyone they made that mistake early on. If you don't pay attention, especially. So usually there's a warning, and the warning could be not only it is very easy to verify that it's not untrue. Just an example, another way to recognize the problem here is to look at the units, and the units don't match. Left hand side and right hand side, the units don't match. So that is why you cannot have that on a more profound level. Why the formula is impossible. It's not just it's naive, but it just cannot possibly be true. We are in a similar position. Once again, if you try to look at the entities of the left hand side, the right hand side, they have to match. So on the left, the product rule, I have the product of two functions, which is another function. Its derivative is a vector field. Okay, so you're supposed to have a vector field on the left and on the right. So if you try to pull something off like this, then you're going to have two vector fields multiplied by each other, which is the only way we know how to. It would be dot product producing a scalar function. So once again, these match. Okay, so the same with the quotient rule. Okay, now with the we just started with the. Where is it? Okay, so with the chain rule. So this one, starting a new topic. Once again, two. If we split the function of two variables or more variables, n variables in the middle, then there are two ways to form composition with it. Either you have a parameter curves before, that is in purple, before the function, or another scalar function after. Okay, so we start with the first one. The illustration is here. So it is a trig map versus a terrain map. Okay, so trig map is a parameter curve, and terrain map is a function of two variables. If you think about it, that is quite a. Why is this important? How do you learn the terrain around you if you're not a bird? Okay, you cannot see, you don't have a bird's eye view, so you cannot fly. What do? You take trips. You take trips around. And what is a trip? It's a parameter curve. Okay, so there you go. So it is a lot of this will be used in order to, you will use parameter curves, traveling around the terrain in order to study functions of several variables. Okay, so that's the terrain which we are trying to figure out. Okay, so and then in the composition now, if we plug in one into the other, the input is time. Okay, so this is should be clear. I want to be clear about that. So this is time. And this is elevation. So the elevation, well, say maybe say 100, 200, 300. These are the elevations in different level curve for each. And so, well, this is just as well. We could have a 100, 200, 300 to indicate that the elevations on the y-axis of our well, in fact, I put z here. I think I always use z for the elevation, which makes sense. I hope you also notice that I have stuck to this convention of using lowercase for numbers or functions of numbers as capitals for vectors or vector functions. So as you can see, that's why over there t f x, t is a number, f is a vector function, vector value function, x is the value, but then f lowercase because the output of that function is a real number z, or once again lowercase. Okay, so and then we guess, and that's the last step we did last time. A guess how do the derivative would form, how would the derivatives of these two functions existing entirely separately. Like this one is a picture, a curve drawn on a piece of paper, and this is might be a reality of actual terrain. Okay, so the derivatives, we know what the derivatives are: parametric curve for the first one, and a vector field for the other one. Okay, so if I try to visualize, it will be a bit hard. So if I try to visualize the derivatives, but that's roughly. Well, I guess I should go in the opposite direction because I'm in the opposite direction, meaning up. I have to move up here if that's what the gradient works like. We're going up the hill. That result hasn't been proven yet, but we are getting close to it. Okay, so that's what the gradient of f might look like. And the derivative, it is not really a derivative of a function of parametric curves. It's not really very expressive. So it doesn't really come out. But well, let me try it maybe. So I'm drawing tangent lines. Okay, I'm drawing tangent lines, even though they should be as like a function of yeah, the best I can do to visualize what derivative parametric curve is like this. So everyone is still a two-dimensional vector, so it is a parametric curve just drawn in this weird way. Okay, so you do not want to do composition of product, composition of these two, but you could do product. So that dot product, and that dot over here is the dot product between them. So vectors, when they align, at the appropriate moment of time, they align, and then you take the dot product of them, and you have your answer, which is just a number. Okay, look at the output function is a number, so its derivative will get a number at every moment of time. It is actually more complicated in a way than to actually guessing and then justifying. It would be harder, but turns out if we just look at it from the point of view of linear functions, it's not so bad. Remember the idea of the derivative of nowadays for these functions is this complex, but there is a point behind it. It is it is linear approximation, okay, and the linear. So we're replacing every function with its linear approximation. As far as that point is concerned, we're looking at it one point at a time. We replace it with a linear approximation, and linear approximation is linear. Okay, so just as well if we do any kind of algebra and we're still looking at the derivative, we could look at the at linear. We're replacing functions with linear functions, and then all of these issues of differentiation become very transparent. Let me give you one example of first of the sum rule. So sum rule we have f and g. Okay, we have the, what does it mean that they have derivatives? So they have linear approximation. Say Lx is equal to p plus mx minus a. Okay, so differentiability, they are differentiable both at x equal a. Okay, and then so that is my one linear approximation. The other one is say k of x is equal to q plus n x minus a. Okay, so two linear approximations where then the derivative, and they point out where the derivative is of each of these functions. These are the ones. So this is del f and this is del g, just for reference. And then what happens if we add these two functions? So add them. So Lx plus Mx plus Kx. And now I rearrange the terms. It will be P plus Q. Well, technically, well, let's just leave it. It's okay. And then I can the two terms that left can be x minus a can be factored out like this. Okay. So what do I have here? Yeah. What?
Be n plus n.
N plus n, yes. Okay, so as you can see, it is a linear function. And everything is, whatever you do is nothing but multiplication, division. There is no differentiation, no limits to worry about. And I just go ahead and circle my my derivative. So this is del f plus g. Okay. So as far as linear approximations are concerned, things work out. So if we want to just stick with two linear functions such as these, and then add them together like that, then you know what the gradient becomes. It was m, and then n 2, and then when we add it together, then whatever happened to the coefficient of x minus a, it is simply the sum of those two vectors. Okay. So that's how the sum rule works out. It's slightly more complicated for the chain rule, but still. So let me write it out. So carefully. So I have my function f capital. Okay, so f capital. So it takes t to what was it? X, and then my function f, a lowercase, is my function of many variables, so it's f takes x to c. Once again, like location on the plane versus elevation, while this is the trig map. Okay, now the composition. Now once again, we're talking about their linear approximation, and this time so we're using linear approximation for the two. So let me write out the linear approximation for f because we just did this. So it will be L of x, x. Capital, L of x, okay, L of x equal to, I'm just copying, p plus m x minus a, with once again this being del f. Okay, now what about the linear approximation of a perfect curve? It's been a while. What does the linear approximation of a perfect curve look like? What is the approximation? There's a curve we approximated with curve. So here we have a surface, and right? And we approximate it with the tangent plane. So function f is a surface in the, say, three-dimensional space, and then we approximate it with a tangent plane at that particular location that we're interested in. Now we're interested in this point. What do we approximate it with? Possibly in multidimensional space.
Tangent vector.
Tangent vector. Tangent vector, yes, but actually it is then it adds up to a tangent line. To a tangent, well, there's no good word for it, but it is indeed given by a vector. But together, the linear approximation is a function, and that the graph of that function is that tangent line. So in other words, we write it as say L. How about L capital? Okay, L capital of t equal to. And now we need to remember what is the parameter. It is still a parameter curve, so both of these are parameter curve. So the approximate function of three variables with function of three variables, and two variables, and so on. You approximate parameter curves with parameter curves. So, but they just have special kind, and this is a special kind is a linear function. So linear. What is the parametric representation of a straight line?
Just all the scalar, all the scalings of a vector.
Right, yeah. So I like to remember it as a point slope formula. So there's a point, say, which is say A, okay, and this is, by the way, point A capital here, which happens to be f of A, okay, and then so it will be then A plus, and then multiples of that vector, say, which is, by the way, called direction vector. So that's why I choose to call it D. And here I have t minus A. The similarity should be striking. The exact same formula, even though the players are very different. So vectors, numbers. Then this is a point. It's another point. And but both of these are vectors. And so I certainly cannot use the same notation. But we remember that it's still the derivative. So we may have different names for it, but it's still the derivative. So this is f prime over here. Well, one particular value of the derivative, which happens to the vector, and happens to be so. That's it. Not a coincidence, but also not a match as much as it is a match in literal sense because they have the same dimension, and we can do something with them. But why do we do anything with them? Very simply, let's see what happens when we substitute. But that's what composition is about. Right, so composition is substitution. So I will just substitute one into the other. This is x. So that x will be substituted in here. Okay. So once again, it's like think about this. It's as if not the general case of us traveling on the terrain. It is the same story, except the terrain is very simple. It's a straight plane, okay, and our motion is also straight line. So imagine this kind of very simple situation. But locally, it is exactly it happens anyway. So every point on that terrain looks like a plane if we are not looking too far ahead, and if we at every moment as we move, we're moving at virtually straight line. Okay, so that's the idea of linear approximation, and here we really take it. We want to really use it. So we assume that this is what's going on there. We have a linear situation altogether. Okay, so as substitute, so what do I have? I have L capital of t. What is it equal to? So I'll do just writing from on the right, p plus m, and x is replaced with that x, which is a plus. Hold on a second. That's not a. This is a capital. Sorry. Yeah. Okay. Now that makes sense. So a is lowercase is the time, that moment of time that we care about, while a capital is the location that we care about. Okay, so then, okay, so what do I have here? So I'm substituting, I'm replacing x with that expression, so it will be a plus dt minus a minus a. Okay, so remember, by the way, I'm skipping very, very quickly, too quickly, but what is this? In the linear approximation of a function of several variables, that is a dot product. That dot over there was defined as the dot product. So remember how we compacted together one derivative into several. It happened some not long time ago. This. Okay, so that is what I'm talking about. Instead of having those making long expressions, we compacted it into using vector algebra into a product of two vectors. One is the vector slopes, and the second is our sort of deviation or step away from point A. Okay, so that's a dot product, and this is still a dot product. Okay, so then we'll see. So that's where the dot product of the chain rule comes from. So A cancels out, and I have P plus M dot product of D T minus A. Okay, and at this point, I just do what I do is I use a certain property of the dot product that T minus A is nothing but a constant, and it can be taken out, factored out of the dot product. So I'll have P plus T minus, I'll push T minus A out, like this, to the right, and I have M dot D. Okay, so rearranging these terms, now what we're looking at is a numerical function. Look at T is the input, a number. That all of these are, this is a number, that's a number, this is dot product of two vectors is a number, so this is just a numerical function. And the derivative is a number. And we do have what we have a number, but where is it? Where is our derivative of this function? Well, compare the expression that we have to those two at the top. So what should I circle?
T minus A.
No.
Just
Oh,
The M dot D, yeah, this one. This is I don't have a name for this function, so let me name it. Say H of T. It is H elevation is a function of time, so that makes sense. And then this is F prime. I'm sorry, H prime. This one. Okay, so that idea of linear approximation can be used for all the functions involved. Composition is doing in a very, very direct way, and then we just by examination we see what our derivatives are, rather than having them explicitly as limits. So this is not a limit, but it's good enough. For linear functions, works out quite perfectly, and you can see how M, those two derivatives right at the top, they're visible there. They're how they end up being dot product with each other. Okay, producing the derivative of a new function. Okay, so certainly this will at the next level would be even simpler than that. Once you taxonomy, if you like, of functions that we have talked about is really too many names, too many functions. While this pretty much we are talking about the same function, just dimension. Over here somewhere there is a function with say 3 inputs, 4 outputs, and its derivative will be what? Well, it's not going to be a vector. It will be a matrix. Okay, so and what dimension? M by n. Okay, so that will be how derivatives come in, and everything turns into nothing but vector algebra. Okay, so another time. Okay, so that's how we find the derivative. How we find the derivative. So it is in the this is just an explanation of why it works based on linear approximation. The formula itself. Well, I probably should just state the chain rule, considering that we have two. So chain rule. I want to write it in a sense, in a way that is kind of ambiguous, but on purpose. So the point is to put it in words in such a way that it will be applicable as much as possible to as many functions as possible, to as many kinds of functions as possible. So the composition of a function differentiable at a point and a function differentiable at the image of that point, or the value of that point. Okay. Let's see. Is differentiable at that point. Okay. And the derivative is the product of the derivatives. Okay, so it is ambiguous. The ambiguity is in many places because we have so many functions and each of them has a seemingly different kind of derivative. This formulation, however, suggests that there is a one general way of looking at them altogether. They are still derivatives, they still behave like derivatives, and they are managed in the same way as the derivatives were in Calculus 1, and this is just one particular case. So once again, if we go to Calculus 1, so dimension 1 versus dimension 1, so one inputs, outputs, 1 and 1, then we know that f composition of g of x is equal to f prime of g of x times g prime of x. Okay, so that's what it means here. So the f is differentiable at the image of that point, so under g. So starting with g being differentiable, okay, let me put an arrow here. Function differentiable at a point, that's my g, that's why it has g prime there, and then the other point is differentiable at the image of that point, which point might be a vector. Okay, so that's the other one. And the function differentiable, so that's the one at the image. Okay, and the product is the product of the derivatives. Okay, so now what we just wrote here is, let me try to, the case of a function several variables and parametric curve, so it will be f, composition f, okay, of t is still f prime, it is del actually, del of f of t dot f prime of t. So that's the formula we just discussed. Okay, so the end result is the product, the dot product. So instead of just in the first line, the multiplication is regular multiplication of numbers, and the second one, these two quantities are involved, are vectors, so you know how you're supposed to handle them. You put a dot between two vectors, you know what it means. It doesn't mean multiplication, it means dot product. Okay, so that's how we know. Okay, so once again, one vector, the other is a vector, so what do? We have, I missed prime, sorry. I have a number. So the result of the composition is still a numerical function, so the answer should be a number. And then there is one more. So f. What if I put f here first? I put f lowercase second rather than first. I just discussed that. Okay, so what's going to happen? It has to be. Remember the metaphor I used for it was we still have a function that represents the terrain. Okay, function of say two variables, and then there is a second numerical function that might represent, for example, the temperature. the temperature as it depends on the elevation, which is totally unrelated issue. There might be, or I have a feeling that there's a fairly steady dependence of the barometric pressure on the elevation. So the air is thinning and thinning and thinning as you move away from the surface, and it's more determined by the how far into the sky, into the outer space you go to actually how far you're off the surface. So that's why mountains are sticking out, and the air is much thinner there, because the layers of the atmosphere with the same pressure more or less go along the general shape of the Earth, and like I said, the mountains are sticking out, and that's why it's so hard to travel and climb the Everest, because the air is so thin. So that's the metaphor, and now so then that is the function that follows our terrain function is so I put it, say, g. Okay, so it's a numerical function. So for a function of several variables, follow the numerical function here. But it is, what's the input?
A vector?
Yeah, ligation. That's right. So what I'm trying to establish is, forget about the prime for now for the time being. I'm talking about the function that presents the pressure as a function of horizontal location. So you give the coordinates on the surface of the Earth, and you want to know what kind of pressure there or temperature, depending on which function you pick. And now we still want to differentiate, and now let's use that verbal description above and try to figure out what the derivatives are. Okay, so we do know that it's going to be two derivatives of these two functions connected with a dot in the middle. So just it remains to figure out what that multiplication is. So g is a numerical function, so what's the meaning of its derivative? It's just the derivative. So it's just g prime of f of x. So then you plug in f into it, it doesn't matter, the derivative will be just derivative. It will be just a number. Then skip over that dot, and now we're looking at f, which is the function of several variables. What is its derivative?
It's another, it's a vector field.
Vector field, it is the gradient. So gradient of f is here. Okay, so of x. Okay, so this is a number, and this is a vector. So what kind of multiplication is this?
Scalar.
Just scalar multiplication, right? So this is scalar multiplication. So this one is dot product. Scalar multiplication, because one is vector, the other one is number, and here is just this number, just multiplication. Okay, so that's how it works out. The same principle applies. If you think about it, it's so widely applicable. At the same time, it is very straightforward in comparison to, if you understand compositions well enough, it should really look simpler than if you compare it to the product rule and the quotient rule. They're kind of complicated and cumbersome formulas. And this is a very direct formula. You have two functions, you have two derivatives, you just multiply them at the end. Okay, no matter what kind of composition it is. As long as you know what the derivatives are, you know how to, the context will tell you how you're going to multiply them. Because there are no other way to multiply them. And I know there's cross product, but I would not put it on the same level as the dot product. So cross product is an exception. It only applies to three-dimensional spaces anyway. So that's how we do it. There is a payoff. So certainly in the chain rule, there's one big there's a point to studying the chain rule, and one is like I said, studying surfaces or studying terrain with parameter curves. So they combine together according to this formula. The most interesting of the three, I think, is this, or at least it is not for now. So the derivative of the composition. So we're traveling around our around our surface, and we want to know the rate of change there. So, so let me step away from it for a moment, or pretend to, and ask the question. I remind you about something that I have been referring to several times, and that is the relation between the gradient and the level curves. Okay, so well, I mean, if you one example that you might remember is f of xy is equal to x squared plus y squared. Okay, so its partial derivatives are 2x to y. Okay, so its gradient is then 2x to y. It is actually a very familiar vector field that we have seen. Okay, so like this. Radial vectors, doesn't really, the magnitude just doesn't matter for this particular example. So these are, make the graph. This is what they look like. On one hand, so that is this is the gradient. Okay. Now, secondly, what about level curves? What do the level curves look like? X squared plus y squared is equal to constant. Set it equal to constant, and then see what that implicit curve is. What is it?
Circle.
A circle. Oh, then there are circles unless it's one point or nothing. So I'll plot just one, just like I've only plotted a few of the vector fields. This is what that circle will look like, and then what is the relation? Remember the relation between the two? It's sort of should be visible. What's the relation between the two?
The one is the tangent when you get it.
No, you know, not tangent, but what?
Oh, just a derivative.
No. What's the angle?
Oh, they're orthogonal. Yeah.
Yeah. So they're perpendicular, orthogonal to each other, and that is the you notice that from observation. You can take, if that's not enough, take a simple example. I think we are pay little attention to that one, but constant, not constant, but linear functions are really very revealing. So I have 2x plus 3y. Okay, then what is the del? My gradient will be easily 2 and 3. Okay, and so that will be then my vector field will be constant at 2 and 3, like this, 2, 3, 2, 3, like this. In the meantime, if I want to have level curves, it will be 2x plus 3y is equal to c, which is what?
Just a plane?
No, it's two-dimensional, it's a straight line. It is a straight line because we are dealing, so level curves of a surface that is in 3 dimensions, level curves are kind of, we push them down into the plane, and they're, as you can see, they're straight lines. You can solve it for y if you like. You have then c minus c over 3 minus 2x, 2/3 x. So as what you can see what has happened to the slope in comparison. Those slopes are 2 and 3, 2 and 3, each of these vectors. And this one has a slope of negative 2/3, which means that this is what they're going to look like. So slope, negative 2/3. So these are all vectors are the same. They're 2, 3. And then the slope is negative 2/3, and then that certainly it doesn't take any effort to actually discover that they're perpendicular. Okay? Or you can just think about the over here, the direction vector being 2 negative 3. Well, or 3 negative 2. 3 negative 2 is our direction vector. Okay, so we have enough evidence to make that suggestion. Before that, however, we have to be very careful about what is that we're trying to say. So the sentence that is described as informally is right here, or right here in black. They being meaning graduated level curves are perpendicular to each other. But the question becomes, what is a level curve? We didn't really define level curves to justifiably call them as such level curves. So level curves are f of x, y equal to c. These are sets in the plane. That's all. It doesn't have to be a curve necessarily. If you take a constant function, what is its level curve? It's not a curve. What is it? So f of x, y is equal to 3. What are these level curves? Three equal to c. What is it?
Is it just a straight plane?
No. Well, literally take it. The function is equal to 3 for every value of x and y. So to set up a level curve, I set it equal to c and one c at a time. So I set it equal to c. For example, pick c is equal to 1. Then 3 is equal to c gives me what? What does this set describe? All x and y for which 3 is equal to 1. What is it?
It's an empty set.
What? It's an empty set. Empty set. So there is nothing. It does not produce anything. Okay, so 3 equal to 2 as well. Nothing again. What about 3 equal to 3?
It's just the set of all x and y's.
It is everything. Yeah, it is the whole plane. So plane, which means that it's not a curve. Okay, so they don't have to be necessarily curves. And if it is not a curve, we don't really know, we can't really speak of angles of other things other than curves or vectors. So if we have a curve, then we know what to do. So what's the answer? So how do we deal with it? Well, we know the tool is a parametric curve. So what we say here is suppose, that's how that algebra works out. Suppose, say, x equal f of t is a parametric curve on the plane. Well, let's start with dimension 1. Okay, and then which stays within the level set. Which stays within the level set, which simply means a level set. Which simply means, it means it's something very simple, a set of our function of f. Of f, so which means simply that the function is constant. So the composition is constant. F, lowercase, of f of t is constant. So that's how we avoid this difficulty of a level curve not being a level curve. So let's just take any curve, parametric curves through that level set and see what happens. And then it is very easy to describe the composition is zero. So it's like we are walking on the I think I this time on the surface, and we are not elevating or going down or up. Okay, we'll finish this.